To the human eye, a skyscraper appears motionless, a monolith of glass and steel resting quietly against the skyline. But beneath that exterior, the structure is engaged in a continuous war against gravity. A building exists in a state of dynamic equilibrium, actively channeling energy safely to the ground. Even on a perfectly calm day, millions of pounds of force travel through this frame, creating constant, microscopic shifts in the material. A modern skyscraper relies on this invisible choreography, the constant balancing and redirection of hidden forces within a frame that appears perfectly poised. To understand how a building survives, we have to look at an engineering paradox. You can construct a tower out of incredibly strong, stiff materials and still end up with an entirely unstable structure. Strength is strictly a material property. It is the ultimate limit a specific component, like a steel beam, can endure before it permanently yields or breaks under a load. Stiffness governs deformation. It measures exactly how much that steel beam will bend, deflect, or compress when a force is applied. Stability, however, is a matter of geometry. It is the structure's capacity to maintain its overall equilibrium and stay upright, regardless of how strong the individual steel beams might be. Strength and stiffness dictate how individual materials behave under pressure. Stability is the master geometric arrangement that decides if the entire structure stands or falls. When a sudden lateral event strikes, a severe gust of wind or an explosive blast, the physics inside the frame change in a fraction of a second. The kinetic energy from the impact slams into the exterior, pushing the massive weight of the building slightly off its vertical resting axis. This diagram illustrates the P-delta effect. Gravity acting down on the displaced structure creates a secondary twisting force, rapidly multiplying the bending moment at the base. This exact threshold of displacement is known in stability theory as a bifurcation point. The mathematics dictate that the structure will follow one of two paths. It will either absorb the energy and snap back to a stable center, or the resistance will drop to zero, sending the geometry into immediate failure. The P-delta effect weaponizes the building's own immense weight against itself. It turns a slight geometric displacement into the structure's greatest vulnerability. If the multiplied stresses at the base exceed the material's capacity, the primary load-bearing column succumbs, instantly losing its ability to support the floors above. This creates a void in the load path, initiating a progressive collapse. The loss of one support sends the weight of the floor crashing down, overloading the floor beneath it, and triggering a cascading vertical failure. In 1968, a gas explosion blew out a single load-bearing panel on the 18th floor of the Ronan Point apartment tower. Left without support, the floors above fell, creating an immense impact load that pancaked an entire corner to the ground. The 2018 Morandi Bridge collapse demonstrated a similar mechanical reality. When long-term degradation finally caused the stay cables on Tower 9 to snap, the structure lacked the ability to halt the chain reaction, taking down massive sections of the roadway. The danger of progressive collapse lies in its asymmetry. The final, devastating scale of the structural failure is completely disproportionate to the small, localized damage that triggered it. Returning to the interior of our skyscraper, the failure of a column leaves thousands of tons of kinetic energy suddenly unmoored. The building has milliseconds to find a new equilibrium. Engineers track how this energy redistributes using a metric called the U-star index, which calculates the relative stiffness of the surviving members to locate the path of least resistance. This visualization maps the U-star index as a glowing river of force. Instead of dropping vertically into the void, the kinetic energy flows horizontally, crossing the concrete floor diaphragms to find intact vertical supports. Safely rerouted, the force travels down these redundant shear walls, completely bypassing the damaged zone to transfer the load deep into the foundation. True structural resilience relies on engineering deliberate, continuous redundancy. When a structure has multiple alternate load paths, a localized break is isolated before it can initiate a global collapse. Reaching the bedrock, the displaced kinetic energy harmlessly dissipates into the earth. The system has stabilized. Viewed from the outside, the massive glass skyscraper remains standing tall, holding its place in the perfectly intact skyline. It survived the extreme lateral event because its global stability matrix was explicitly designed to outsmart localized physical damage. But as we move from the deep foundations to the upper atmosphere, structural integrity faces an entirely different set of physical laws. Keeping a tower upright against gravity is only half the equation. The next challenge is surviving the chaotic, high-altitude forces of extreme wind.